Today we will discuss velocity kinematics and statics, and we will discuss about joint velocity. They are rotating, that is rotational power is converted into translational power of tip point. Consider this hand, this human hand, as a 2R planar robot. So this joint here and this joint, suppose we are rotating this way, so we are giving power to this tip point. This rotational power is converted into translational power this way. See here, force into velocity, F tip transpose into V tip equal to tau transpose into theta dot. It is omega, angular velocity. Now initially we will discuss the Jacobian also plays a central role in static analysis. Suppose an external force is applied to the robot tip. What are the joint torques required to resist the external force? This question can be answered via conservation of power argument, assuming that the negligible power is used to move the robot. So we require negligible force just to move. The power measured at the robot's tip must equal to the power generated at the joints. Denoting the tip force vector generated by the robot as F tip and the joint torque vector by tau, the conservation of power then requires that, see here, we know that dot product of force and velocity gives translational power, generally mechanical power. F tip transpose, in this book all vectors, force, velocity, torque, all are column vector, but we require dot product, so transpose is taken. So F tip transpose, this is force acting on tip, into velocity tip, it gives translational power, and tau transpose into theta dot, it is d theta by dt, it is angular velocity, and we know that torque tau dot omega is rotational power, that is rotational power is converted into translational power. I am giving the proof for this. We know that power P is dw by dt. This dw is a very small work, dw by dt. It is not angular velocity, it is work, dw by dt. But dw is f dot dr by dt. So dr by dt is v, so f dot v. F dot v is nothing but fx dx plus fy vy plus fz vz, dot product between these two vectors. And for this, power P is f dot v, but v is omega cross r. V is linear velocity, is angular velocity cross position vector. So P is f dot v is replaced by omega cross r. So we can change the order, cyclic. F dot omega cross r, it is box product between f, omega and r. So we can write this way, omega vector dot r cross f. This way, reference for three vectors a, b and c, a dot b cross c, it is the box product between a, b and c, equal to b dot c cross a, cyclic order a, b, c, b, c, a, c, a, b, all are same, b dot c cross a equal to c dot a cross b. After taking values symbolically, you can prove this. So it is box, sometimes box product denoted as box of a, b, c, b, c, a, c, a, b. For cyclic order, the value remains same. So here we can change order, f omega rf. So omega dot r cross f, but r cross f is tau. Omega here, this one, is angular velocity. So omega dot tau, r cross f is tau dot tau. Omega is angular velocity, but in dot product order is not important. So tau dot omega, and tau dot omega is angular velocity, it is theta dot d theta by dt. So this power, this one, tau transpose into theta dot. In matrix, this one already dot product is there. Now for all arbitrary joint velocities, theta dot, that is d theta by dt, since v tip equal to Jacobian of theta into theta dot. Go through our previous lecture. We have discussed about Jacobian in depth. So velocity of tip is Jacobian of theta into theta dot. The equality F tip transpose, but velocity, this velocity of tip is replaced by this J of theta into theta dot, which is equal to tau transpose into theta dot. But this theta dot cut out, and if we take transpose both the sides, if we take after cutting this one this way, F tip transpose into J of theta equal to tau transpose, and then after F tip transpose J of theta, taking transpose both the sides, tau transpose further transpose, we get this one. This can only be true. Tau is tau transpose, so tau, and F tip transpose J tau theta transpose, order is changed. So J theta transpose into F tip, it is equation 5.3. Just writing here, J transpose theta into F tip is tau. Now multiplying both the sides by J transpose theta inverse, left hand side. So this one, J theta transpose inverse into J transpose theta into F tip equal to, left hand side we have multiplied, so J theta transpose inverse tau. But this product inverse and this matrix, it is identity matrix, so I into F tip is this one, so F tip equal to J theta transpose inverse into tau. Sometimes this symbol is denoted as J theta minus t, but inside it is J of theta transpose inverse into tau. This is 5.4. Using the equation above, one can now determine under the same static equilibrium assumption what input torques are needed to generate a desired tip force. For example, the joint torques needed for the robot tip to push against a wall with a specified normal force. Now we will take example for the manipulating ellipsoid, torque tau and force. Okay. Today we will discuss mapping joint torque bounds to tip force bounds for a 2R planar robot with initial posture. This link, first link, it makes 0 angle, theta 1 is 0, and this link makes theta 2. So for this initial posture, we are mapping joint torque bounds to tip force bounds. So torque at this point and torque at this point, tau 1 and tau 2, tau 2 versus tau 1. If tau 1 in between minus 1 and 1 or between them, and tau 2 is also, then what about the range of force, that is force bounds F1 versus F2. We have formula F tip, we have discussed already, transpose of Jacobian theta and inverse into tau. So this is J of theta, this is J of theta. We have discussed in depth in our previous lecture. This one minus L1 sin theta 1 minus L2 sin of theta 1 plus theta 2. Here minus L2 sin of theta 1 plus theta 2. L1 cos theta 1 plus L2 cos theta 1 plus theta 2. L2 cos theta 1 plus theta 2. Transpose and then after inverse into tau 1 tau 2. But for our initial posture, theta 1 is 0 and theta 2 is pi by 4. So substituting this value in this matrix, we get sin 0 is 0, sin pi by 4 is 1 by root 2. So we get minus 1 by root 2, minus 1 by root 2. Here cos 0 is 1, L1, L2 we have taken 1 both. So 1 plus 1 by root 2 and this one is 1 by root 2. Transpose of this matrix and then after inverse into tau 1 tau 2. So F tip, if you take transpose of this row becomes column and this row becomes second column. So here f tip equal to minus 1 by root 2 minus 1 by root 2, 1 plus 1 by root 2 1 by root 2 inverse into tau 1 tau 2. So f tip equal to inverse matrix for this I have calculated rough and placed here 1 minus into bracket 1 plus root 2 1 minus 1 tau 1 tau 2. So f tip is this. First row, this column, we get tau 1 minus 1 plus root 2 into tau 2. It is x component of force, and this one into this one, tau 1 minus tau 2, it is y component of force. So here, if tau 1 is 1 and tau 2 is 1, that is this point. 1 comma 1. This one is minus 1 comma 1. This one is minus 1 comma minus 1, and this one is 1 comma minus 1. So if we put turn by turn here, corner points, tau 1 is 1, tau 2 is 1. If we put here, f tip we get minus root 2 comma 0, which is point A. Tau 1 is minus 1, tau 2 is 1. And if we put this and this, we get f tip equal to minus 2 minus root 2 comma minus 2, this is point B. And if we take tau 1 is minus 1 and tau 2 is also minus 1, f tip is this root 2 comma 0. You can check yourself. And this represent point C, and if tau 1 is 1 and tau 2 is minus 1, f tip is 2 plus root 2 comma 2 D. So here I have drawn the figure with great accuracy, 1, 2, 3, and this one x component is almost 3.414, and we get 2 plus root 2 is exactly 3.414, and the y coordinate is 2, so this point has y coordinate 2. Similarly, this. So here, this and L1 and this tip, this is tip. So we can achieve force at that posture in all direction, but the constraints of magnitude. We can give force in this direction, we can give force in this direction, we can give in this force in this direction, but this much, not this much. So this graph is mapping joint torque bounds to tip force bounds. That's it. Now another example with different condition. Mapping joint torque bounds to force bounds. But here, torque tau 1 and tau 2, the range follows tau 1 square plus tau 2 square equal to 1 unit circle. In our previous example, we have taken tau 1 and tau 2 both minus 1 and 1 or between them. But here we are changing the condition. If tau 1 and tau 2 is applied in such a way, tau 1 square plus tau 2 square is 1. And the same example, so f tip is tau 1 minus 1 plus root 2 into tau 2, tau 1 minus tau 2. It is the x component of force, this is y component of force. It is generally denoted as f1, but it is fx also. So tau 1 minus 1 plus root 2 tau 2, and fy is tau 1 minus tau 2. This one, I want to eliminate tau 1. So subtracting these two, minus, plus, minus. So fx minus fy, this is cut out. And plus tau 2 minus root 2 tau 2. So here minus root 2 tau 2, fx minus fy. So tau 2 is fx minus fy by minus root 2, tau 2. Now this tau 2 is substituting in this equation, fy equal to this one. We get fy equal to tau 1 minus tau 2. Therefore fy equal to tau 1 minus tau 2 is this, fx minus fy upon minus root 2. So minus minus plus, and subtracting tau 1, we have fy minus into bracket fx minus fy by root 2. But tau 1 square plus tau 2 square is 1. And tau 1 is this. So fy minus fx minus fy by root 2 whole square plus tau 2. Tau 2 is this. Fx minus fy by minus root 2 whole square equal to 1. So expanding this, fy square minus 2fy into fx minus fy by root 2 plus this square, fx minus fy by root 2 whole square plus fx minus fy by minus root 2, but square is there, so we can write plus root 2 whole square equal to 1. So fy square cut out, minus root 2 fy into fx minus fy. here squaring these two terms are identical, so 2 into this one of the square, and root 2 square is 2, so 2 cut out, and the square of this is fx square minus 2fx fy plus fy square equal to 1. Now expanding, multiplying this, fy square minus root 2 fx fy plus root 2 fy square plus fx square minus 2 fx fy plus fy square. So rearrange terms, fx square, and here fy square there are three terms, one, this and this. So fx square and fx fy is this two. So it is fx square minus this and this, so minus 2 plus root 2 fx fy, and this one are 2 plus root 2 fy square, 2 plus root 2 fy square minus 1 equal to 0, this one. So here fx square minus of 2 plus root 2 into fx fy plus 2 plus root 2 fy square minus 1 equal to 0. Again fx square minus into bracket 2 plus root 2 fx fy plus 2 plus root 2 into fy square minus 1 equal to 0, which is an ellipse. This is the equation of ellipse. You can consider fx as x, and this one is this is the equation of ellipse in 2D. So which is an ellipse f1 and f2, and this is 2R planar robot, L1 L2 both are 1. So this is force ellipsoid. For this condition tau, the force is this way. So here for tip at that posture, this posture, we can give force in this direction, in this direction, in this direction, but in this direction, suppose this one at an angle theta, this one. So we can maximum give this much of force, not this much. So under certain magnitude constraints, but we can give force in all directions here. But for singularity, this ellipsoid converted into a single line.